All right, take it away.
Thank you. Good morning, everyone. My name is Prasanna, and I work for the personalization infrastructure team at Netflix. And I have DV with me, who works on the algorithmic engineering team at Netflix. At Netflix, we aspire to a day when our members can turn on Netflix, and the absolute best content for them has already started playing for them. While we are far away from this goal, it sets us a vision for us to improve our algorithms that span our service. So where do we use algorithm in our service? Literally everywhere. As you guys might be aware, the videos that we show in your homepage and the ordering of those videos are personalized for you. And so are the rows themselves, and the ordering of the rows are personalized for you. Roughly around 80% of what our members watch come through recommendations, which is driven by machine learning algorithms. So how do we improve our machine learning algorithms to realize our grand vision? Just like everything else at Netflix, we follow a data-driven approach to improve our algorithms. As a first step, we try an idea using historical data as part of offline experimentation and see if we have made better recommendations than the existing ones. And if it did, we would then deploy it to a live A/B test to see how it performs well in production by looking at various core metrics such as member retention, member satisfaction, and member engagement. Now, reducing the time from inception of an idea to deploying it to a live A/B test is a key metric that we use to measure the success of infrastructure projects at Netflix. So to that end, we built a time machine using Apache Spark that has greatly reduced this time from idea to production. The rest of this talk is going to be, why did we build this time machine? How did we build this time machine? And how did we use this time machine for feature generation? Now let's look into why did we build this time machine. The main motivation is to quickly try out new ideas using historical data and be able to quickly transition from an offline experimentation to an online A/B test in a seamless fashion. That is the primary motivation of building a time machine. So how did we generate features in the past? There are various ways to approach feature generation, one of which is to generate features based on Hive data. So you could read data from Hive and generate features for a time in the past. The biggest disadvantage with this approach is that once we decide to transition this idea from offline experimentation to an online A/B test, we need to re-implement features because we now have to read data from an online source rather than reading data from a Hive table, which we did from an offline experimentation. And as you folks know, whenever we replicate business logic, we might run into various software bugs. The other disadvantage with this approach is that not all data is available offline. For example, the output of recommendation models, which usually takes in a very sparse input and produces a dense output, is not available in an offline source. And whenever there are data discrepancies between online and offline sources, we might run into differences of output in model generation. We've also tried the other extreme of logging features where the models will be used. Now, while this reduces or in fact removes the complete discrepancies between online and offline source, this has a major disadvantage that you need to deploy each idea into production, wait for the data to be collected, and then check if the idea is doing good or not, which is not an ideal scenario either. We've also tried a common middle ground where feature generation calls online services and filters data that is passed a certain time. Even this approach reduces or removes any discrepancies between online and offline source, but this only works for services which maintains a history of the service records or historical events. And not all services at Netflix have that history. The other disadvantage is that this approach adds additional load on online services. So when our research engineers runs feature generation, we have additional load to online services. So when faced with such tough problems in your life, what would you wish you had to solve them? Anyone? A time machine. So that's exactly what we did. We built a time machine which snapshots data from various online services and uses that snapshot data to generate new features in offline experimentation. So when research engineers design new features, they can immediately use them to generate features for a given time in the past. So this greatly improves our speed of trying out new ideas and increases agility and pace of innovation. This approach also removes any data discrepancies between online and offline sources. We also share facts and features between experiments without calling the live system. So that means when feature engineers and when research engineers design new features, we don't have to go hit the online systems, which is a good thing. Now that we have seen why did we build a time machine, let's focus on how did we go about building this time machine. There are various steps involved in building a time machine, the first of which is what is called a context selection. Now, what is a context? It is the setting for evaluating a set of items that needs to be ranked. For example, a member profile ID and a country together is a context. The output of this step is to just figure out the list of contexts or a set of contexts that needs to be snapshotted. The next step in building a time machine is to snapshot data from various online services for the selected context. And the last step is to build an API that can rewind time and do the time travel. Now let's focus more on context selection. Snapshotting data for all contexts is a very expensive operation. So we choose only a subset of samples for snapshotting on a daily basis. But different experiments require different distribution of context. So we choose a stratified sample of our member profiles for snapshotting data on a regular basis. And this stratification can be based on various properties such as member viewing patterns, what country they are in, what device are they in, and how long have they spent time using our service. Finally, we merge the merged context in S3 and tag them with appropriate metadata such as what's the A/B test identifier that is used to select a particular context. So the output of this whole process is just to select the list of contexts that needs to be snapshotted. The next step in building the time machine is to snapshot data from various online services, such as a member's viewing history, or many other online services. Now, as you folks might know, Netflix embraces a fine-grained service-oriented architecture for our cloud-based deployment model. Netflix almost runs entirely on AWS. And there are hundreds of such microservices that are collectively responsible for handling a user-facing request. Services such as viewing history, my list service, or a rating service, the data of which are used as input to the features for feature generation. We use a lot of Netflix-specific components to fetch data from these online services using their respective client libraries. Now, many of these client libraries bulk load data so that it's useful for producing low latency in real-time request. Spark is not well suited for loading these components because these components require or use a high memory footprint and take a long time to boot up. Spark is not well suited to load these components into its JVM. So we used Prana, which is a Netflix open source data proxy, which is built on top of the Netflix ecosystem and is put out separated out from the Spark JVM. Spark parallelizes the calls to Prana, which in turn fetches data from various online services. We chose Thrift as the binary communication protocol to communicate between Prana and the Spark slaves. Finally, the output of the snapshot data is stored in S3 in Parquet format for both time and space efficiency. We also store the S3 location of the snapshot data in Cassandra. The last step in building the time machine is to build an API that can rewind time and do the time travel. So when given a timestamp, the API fetches the data from Cassandra, the S3 location from Cassandra, and loads that snapshot data into Spark. Additionally, when given an A/B test identifier, the API filters out the snapshot data only for those members in that A/B test. But more importantly, the API also transforms the snapshot data into the respective services POJO objects, plain old Java objects. Now, why is this critical? This is critical because we don't want to re-implement feature encoders when we try out a new idea in offline experimentation and then do a live A/B test. So let's bring this all together. The first step in building the time machine, as we all saw, was to identify the set of contexts that needs to be snapshotted And as we spoke about, we have a stratified sampling of identifying the member profiles that we need to snapshot. The next step is to build the online services and fetch data from these online services and snapshot the data and store them into S3. The final step was to build APIs that can do the time travel and fetch data of the snapshots given a timestamp in the past. Now, we had to schedule several Spark jobs for both context selection and data snapshots with possible dependencies between them. And what I mean by that is the output of the context selection process is then used as the input for the data snapshot Spark jobs. So to that end, we built a general purpose workflow orchestration and scheduling framework called Meson, which is optimized for machine learning pipelines. We intend to open source Meson and talk more about it in the coming months. So now that we have spoken about how did we build this time machine, I would like to invite DB, who would go over how did we use this time machine for feature generation. Thank you.
I'm DB. I'm a research engineer at Netflix, Spark committer. So, what is the... We built DeLorean at Netflix. This is an internal project. We use, DeLorean is an internal project we use, which can take an experiment plan, and then we can travel back in time to collect all the necessary data from snapshot, and then create a feed as if we are at the given times. So why travel back to the time is important? Yeah, because recommendation system is basically an analytical process. So basically, recommendation system is an analytical process to learn from the past to predict the futures. As a result, each given past event, like the watching history, we need to create a features right before that times. Otherwise, we are predicting the current data, current play using the feature data. And not only time traveling is important, we also need a scalability. Spark gives us the scalability such that we're gonna be more confident on our experiment results, and also we can iterate more ideas given the same time. Also, we can easily prototyping the new idea using notebook. And this allows experimental or data scientists to quickly iterate from different ideas, trying out different feature engineering or different algorithms. And finally, the key success of the project is that we want to make the logic between online and offline feature generation being shared. So literally, when a data scientist implements some feature in the offline experiment, we can bring this same logic to the online systems. So how do we run the, time travel experiment? Of course, we need to select a destination time in the beginning, and then we can bring it to 88 miles per hour. Of course not. Okay, so here is the highlight diagram about how we run the experiment. First, data scientist has to design the experiment by designing which feature they want to use or which machine learning algorithm they're gonna use. And then we can collect the label data, which is the watching history of a certain members. And that can be done by a Spark SQL query from our Hive tables. And we use DeLorean to do the offline feature generations. And we either use distributed machine learning algorithm in Spark ML, or we can use different multi-thread single machine algorithm and train them in different executor to parallelize the training process in order to do the parameter searchings. And we can compute a validation matrix from all the models we trained. And we pick up the best models. And then we can compute the testing matrix. And we compare against the testing matrix and our online production experience. And if the matrix doesn't look good, I mean, compared with the online version, then we can go back, redesign the experiment based on the experience we learned from the whole process. And this is the whole offline experiment part. And if the matrix is good compared with the online experience, then we're gonna deploy it into the online system and do the online A/B testing. And in general, we don't load it out like broadly. We only load it out to selected context, which means we only load it out to selected users in certain countries or selected users in certain devices. Of course, the whole offline experiment is done in Spark with Notebook. Okay, so what is the DeLorean input data format look like? So we need to decide what is the context first, and context is the minimal building block of a ranking problems. So how does it work? So each context is gonna contain a set of the items, and item gonna be the stuff you're gonna rank inside one context. So for example, like a user in certain country, he gonna have items, and all the items gonna be our available catalog of videos in that particular countries. And that's why we need to have countries as part of the context, because in different countries, we have different catalogs. And we have labels, it's for supervised learning. And we, in general, create label from the Hive queries. And then we can train the model by learning the supervised learning model, which gonna predict a given title, what is the probability that a member gonna play that particular video at time t, given a feature as t prime smaller than t. So that's basically what we are doing. And feature encoder is the way that we can transform the features from the POJO or the raw elements into the features. And it's gonna compute for each context item combination, you're gonna compute one of the features. And each feature encoder has its own data key associated with it to be an identifier. And each feature encoder has a way to return all the data key they're gonna consume, which means each encoder can return which data they're gonna pull from the snapshot. And DeLorean uses it to create a data map. And data map gonna be the key to the POJO object for each context. So for each context, we're gonna create one data map. So we're gonna explain it later. Okay. So we have two types of data elements. And one is context dependent, the other is context independent. And for context dependent one can be like a viewing history or like my list, and viewing history is different for each different context, of course. And context independent one can be like a video metadata. So they're gonna be shared for all the contexts. Okay, so here is an example. We want to compute a feature which is for a target video in item. What is the fraction of the watch, video history that gonna match, that particular country of the orange? Okay. So we have a context item here. So basically, to simplify the problem, I don't have the country here. So we have 2 users and 3 items to be ranked. And you have context-independent data element, which is the video metadata. So for each video, you have the country of the orange. And you have context-dependent data element, which is the viewing history. So you can see for Martin, he watched Back to the Future and IP Man. And for Dr. Brown, he watched Terminator and Back to the Futures. Okay? So the first feature you want to compute is that you need to pull in the context item, and then for each of them, you need to join all the data elements in order to compute the features. Okay? And for the first video in the Martins, which is Back to the Future, okay, Back to the Future in the items is American movies. And he's watching history, he watched 2 videos. Okay, and one of them is American, the other is Chinese. So basically 50% of the watching, is in American movies. And the same way, I mean, for the Chinese one, 50% of them are in Chinese. And the final one, also 50%, because the final one is the American movie, and based on the watching history, he watched 50% in American movies. Okay, so how about for Dr. Brown's? So the first one gonna be 100% because he only watched American movies. And the second one, IP Man, which is Chinese, he never watched any Chinese movies. And the third one is also 100%. So we and content in a different ways. Can you guys hear me? Okay. And for the context independent one, we actually broadcast it into each executor as a singleton because those data tend to be really small. Okay, and this is the overall picture of how we do feature generation. So once data scientists decide the label data and also the feature models, which gonna contain all the feature they're gonna use in the feature encoders, and he may implement new feature encoder as well. Okay, and then DeLorean gonna pull in the feature models and know which feature they're gonna use. So it's gonna call the feature encoder library and see the join of the data key. And only those data gonna be pulled into the DeLorean system from the data elements. And the data gonna be sent to a DeLorean in a POJO format. And DeLorean gonna construct the data map, which gonna be a key to the actual POJO map, send it into the feature encoder, and feature encoder gonna return the features. And then we have the training features or testing validation set right now. Okay, once the feature is generated in Spark, we actually represent it in a Spark data frame format. And we make it as a nested structure to avoid shuffling when we do ranking. Because lots of time when people do ranking, it's ranked within one context. And if you don't make it nested and make it like a flattened structure, you're gonna do a really big group by, and that is really expensive. And for feature experiment using the same features, the final results are stored in S3 using Parquet format. Okay, so here's the schema of our features. As you can see, the feature, visitor and country are the context. And then you have in each context, you have a nested structure of a bunch of the items. And items here gonna be the video IDs. And you have the label and features in this format. Okay, so how do we go online? So as we already talked about, we train the whole offline experiment using Spark, and then you implement some feature encoder. But in online world, we actually use the same feature encoder to avoid the discrepancies. However, in online world, we don't do the snapshot. We get the data directly from the online microservice. And then with the feature, we can use the model, build it in offline experiment, and then do the ranking process. And finally, we can do an A/B testing for a given selected context of the users. And of course, the final ranking result is also a service at Netflix. So we may store them back to S3, snapshot it, such that different experiments can use it as an input. So conclusion, by collecting all the state of the online world at a given point in time, it allows us to build a machine that can travel back in time to generate a feature in the past, instead of waiting a couple days to collect the data. And DeLorean right now is being used for production for several A/B tests right now. And also it's allow us to iterate faster from idea to A/B test. And we can try out more different ideas to improve our user experience. And the future work, so it's not just a start. So we have a lot of work we're gonna work on. So there are many ways we can snapshot the data. We can snapshot it by event-driven to avoid duplication, or by snapshot the data, which we can help us to save some space instead of doing a full snapshotting. And of course, we have the ability to travel forward in time, so we can exactly know what you're gonna watch. So this is gonna be our next work. Okay, thank you. And by the way,
So we're going to open up the floor for questions. So if you have a question, just go ahead and raise your hand. I'll walk over.
In your concrete example, you use 2 users. So the snapshots, I assume, are for specific users?
That's right.
And do you then slowly rotate them out so that you sample, so you have some loss if you want to go forward in time, but it's small enough that you get valid
That's right.
results?
The sample size is big enough, and we have a time variance into that.
Thank you. It's a very good presentation. My question is around the privacy. How do you manage the privacy of customers?
None of this is, it's all in our cloud. None of this is exposed to any of the public clouds. And we use member ID as, which is being rotated every time after a year or so when our members leave our service. So none of this data is exposed anywhere outside of Netflix. Yes? So the question is, what's the criteria to decide if an A/B test is successful or not?
Yeah, so basically for A/B testing, we are looking at like a streaming hours, retention rate, or like a customer satisfaction. But in order to bring it like from the offline experiment to the online experiment, we are looking at like a traditional like a ranking metrics, like MNR, recall, this type of stuff. So we often found that it's not really, sometimes it's not correlated. So you can pump up the, the training metrics, but sometimes it doesn't reflect in the A/B testing. So that's why we still need to do A/B testing in order to validate if the model works or not.
I was wondering if you use, Spark's feature encoders, or Netflix has its own custom feature encoders. Do you use Spark's, or do you use a combination of both?
Yeah, so Netflix has our own feature encoders because we already have a system built online to generate the features from the microservice data. So basically, it's our own implementations. Yeah.
We're going to have to move on to the next talk, but I'm sure the speakers would be happy to take questions offline. If we could please give them another round of applause.